Hi everyone, we have already seen that in predicate logic, there are two types of statements, the instantiated statements and the quantified statements. An instantiated statement is achieved by applying a predicate to a constant in the domain of discourse. Thus, each instantiated statement concerns only specified instance in the domain of discourse. On the other hand, a quantified statement involves quantifiers and variables. Each quantified statement is about what will happen as a variable ranges through the domain of discourse. Thus, they are of different nature, yet both of them are very important. We have already explained that when the domain of discourse contains infinitely many elements, it is impossible for us to reconstruct quantified statements using merely instantiated statements and connectives. On the other hand, when we work on deduction, very often we got to carry out some operations. We might want to add two real numbers. We might want to rotate a triangle. Most of these operations are applied directly to concrete instances instead of to the domain of discourse. In other words, they concern instantiated statements. Thus, in today's section, we will discuss two types of rules of inference that permit us to move back and forth between these two types of statements. More precisely speaking, if you start from a quantified statement and you want to derive an instantiated statement, you will need a rule of instantiation. To the contrary, if you start from an instantiated statement and you want to conclude a quantified statement, you will need to use a rule of generalization. We will start from the rules of instantiation. The rule of universal instantiation tells us that for all x px, we can derive pc for an arbitrary constant c in the domain of discourse. The existential instantiation, on the other hand, tells us that for some x px, we can derive pc for some fresh constant c. Be careful, when you are applying the universal instantiation, you are given the right to choose c at your preference. However, if you're applying the existential instantiation, you are not given this right. Here, c must be a fresh instance, meaning that we should treat this c as a stranger that has never shown before. We know absolutely nothing of this instance except that pc holds. For instance, let D be the domain of discourse representing all cats, and px be the formula that x is a ginger cat. Now, if we start from a universal statement saying that every cat is a ginger cat, from there, I can derive that my own cat, Chui, is a ginger cat. I might have a particular motivation to choose my own cat, and I was given the right to do so, right? Maybe my cat is particularly lovely, a little bit naughty, or for any other particular reasons that you want to keep going with this specific instance, then go for it. There's no problem. On the other hand, if you are given the statement, there exists some ginger cat. What can I say from there? I can derive that a cat, namely Trudeau, is a ginger cat. And I choose this name because this name has not yet shown in my deduction process. Thus, it is a fresh name. And what I know at this moment is that Trudeau is a ginger cat, but that's all what we know for Trudeau. Is it smart or lovely? I'm not sure. Neither do I care. And hopefully this gives you an idea how these two rules of instantiations are actually in sharp contrast in application. Next, let us move to the rules of generalization. A rule of generalization permits us to start from an instantiated statement and arrive at a quantified statement. Similarly, there are two such rules. The first one is called the universal generalization. It tells us that if we start from an arbitrary element in the domain of discourse, and from there we show that pc holds, then we are allowed to claim that for all x px holds. On the other hand, we have the rule of existential generalization, which tells us that to show for some x px holds, it is enough to pick a specific c and show that pc holds for this very instance. Again, one should pay attention to their subtle differences. In the universal generalization, when you work on pc, this c should be a generic element which does not have any extra property other than the fact that it is an element in D. However, to apply the existential generalization, you can choose the element c to work with at your preference. You can assume extra properties to this c as long as it remains in D. Using the previous example for instance, suppose that you want to conclude every cat is a ginger cat. You should take a generic representative, call it c, for example, and show that c is a ginger cat. You are not allowed to assume, in addition, that c is a British Shorthair or c is a Siberian forest cat. The only thing you can say is c is a cat. That's it. That's the only condition you have, and from there you got to show that c is a ginger cat. On the other hand, if you want to apply the existential generalization, you are given the right to choose the specific cat that you want to work with. If you want to add some extra assumptions on that cat, as long as it can make your deduction easier, go with it. There's no problem. The only constraint is that this instance must still remain in the domain of discourse. That is, it must still be a cat. But other than that, you are totally free to choose an instance that might give you some advantage. As long as we can show that PC holds for this particular instance, we can derive from there that for some x, px holds, and our mission is complete. Finally, let us recall an example that we have used when we explain the limitation of the propositional logic. Let us consider the following statements. Every cat is lovely. Tree is a cat. Therefore, tree is lovely. We have explained how the deduction does not follow directly from modern ponens, and we will need some extra rules of inference related to the quantifiers, which we achieved now. So let us rewrite it in a language of predicate logic. To this end, let us assume that D is our domain of discourse, which contains tree as an element. P stands for the predicate, is a cat, and Q stands for the predicate, is lovely. Thus, the whole statement is translated into the following. For all x, if px, then qx. Now, since tree is an element in the domain of discourse represented by C, we can apply the rule of universal instantiation and conclude that if pc, then qc. Moreover, since tree is indeed a cat, pc is true. Thus, we're ready to apply the modern ponens and conclude that qc is true as well. That is, tree is lovely. This simple example demonstrates how a proposition that is not derivable in the frame of the propositional logic can now be easily derived in predicate logic.